Okay, so like I was saying, I'm going to start this introduction where I present the problem in robotics that we are trying to solve. Then I'm going to formalize the problem and present our approach, how we implemented, and finally some results and conclusions. Okay, so I will start this presentation by bothering you with some terms in robotics. And the first one is navigation sensors or proprioceptive sensors. There are sensors that are used to acquire information about the robot itself. So we have speed, acceleration, and many others. Then we will also have observation sensors or exteroceptive sensors. There are sensors that are going to acquire information about the environment surrounding the robot. So we have cameras, sonars, lidars, and we have other examples. Okay, so as you can see, we are interested in the problem of an autonomous underwater vehicle, or AUV, that explores an unknown environment using two side-scan sonars. And what are those? So side-scan sonars, they are sensors that are used to create an acoustic image of the seabed under the robot. And the advantage of using sonar instead of cameras on the water is that the acoustic image will not depend on the light available and neither on turbidity of the water. So here on the right, we have a real image that was acquired by two lateral sonars. And we can see that we have this black band in the middle. You can see it, yes, that corresponds to this gap that we have between the two sensors. So from where we have no information. And then we can see the seabed with its textures on the right and on the left side of the sonar. And these images, they are usually called waterfall images because as soon as new data arrives, the current image shifts downward. I don't know if you'll be able to see. Yeah, so like a waterfall. Okay. So in this work, we will be considering that the gap between the two sensors doesn't exist. So we will be adding a gap filler. So this means that at any moment, the robot's visible area would be something like this green line that we have over here, that is sensing a narrow portion of the environment. Okay, so now let's imagine a simple mission where the robot only moves forward. So in these missions, we will have that the union of the visible area over the whole trajectory would be the explored area during this mission. So here in this example would be this green rectangle projected onto the seabed. And our objective in this work is to estimate the explored area and also to determine how many times each point in the space was sensed or was seen by the robot during exploration. And we call this measure the coverage measure. And we want to estimate this using only the information that comes from the proprioceptive sensors. Okay, so why do we want to do this? So first, we want to calculate the explored area. And the main application is to assess area cover emissions. So an area cover emission is a mission where the robot is required to cover with its sensors or tools a whole area of interest. So if you have autonomous vacuum cleaners in your home, you probably already saw this. But the underwater environment, we will be using these missions in the search of wrecks, to do hydrographic surveys, and also in the search of potential threats like underwater mines. And if we can estimate the explored area, we can determine if these missions are completed, and we can plan other missions to fill possible covering gaps. And the coverage measure, I'm going to be citing 3 applications. So the first one is the simple one, that is to plan optimized trajectories. So if we don't want to pass through the same place twice, remembering that the coverage measure is how many times each point was seen by the robot. And then for the next 2 applications, I'm going to be using some graphics. Okay, so first, here we have localization in homogeneous environments. So I'll briefly explain how usually algorithms of localization work. I mean, there are several algorithms of localization, but they can work like this one. So first we do what is called proprioceptive estimation. So we are going to be integrating the information that comes from the proprioceptive sensors. So acceleration, speed, and angular velocities. And we will obtain a first estimation of the robot's position. So as you can see here in the picture, we have this black line that corresponds to the robot trajectory, the actual robot trajectory that we don't know, that we are trying to estimate. And then we have this blue envelope surrounding the solution. That is what we can estimate with the proprioceptive sensors. So at the beginning, it can be very accurate if we know where we are. But then as we propagate error through integration, it becomes less accurate. And then here what we can do what is called exteroceptive update. So it's when we take information that comes from the exterior, about the environment, and we try to do feature matching. So we will be trying to determine that we are in a place that we've been previously. And at this moment, we can refine our estimation around the loop. So this technique is called loop closure. And if you are in a place that have a lot of features, this will be very easy. But in the underwater environment, that is a homogeneous environment, it will be very hard. So here, for example, I have 5 pictures that were acquired by a lateral sonar of 5 different rocks. And as you can see, they look very much the same. So all the algorithms of feature matching that we have today would probably say that they are the same. So we are in a place that we've been before, leading to a bad exteroceptive update. So, however, if we know that 2 of these pictures were maybe acquired around the region that was sensed twice by the robot, we could use this as confirmation that we actually had a loop closure. And that's how the coverage measure could add. And then for the other application is for what I call SAS Revisiting Missions. So this is a problematic that was posed by the French Defense Agency, DGA, to the ROBEX team. And to understand it, I think it's better to look at the image. So we have this image of 2 lateral sonars. And as you can see, well, you can see very clearly, but we have some rocks, we have some debris, and we have an underwater mine that was detected. So I don't know if you can see, but it's very hard. Sonar imagery is very hard, and you need to be an expert to detect an underwater mine. So when they are doing area covering missions looking for potential threats, they want what is called mine-like objects to be covered by the robot many times and not only once to help in the classification. Okay, so now I will quickly formalize the problem. So in this presentation, we are assuming that the robot's trajectory is known. In the paper, we will be dealing with uncertainty in localization, but here we assume that the robot's trajectory is a continuous function in the plane X that we know. We will also be defining the visible area of the robot that, as we said, will be a fixed size line that will only depend on the robot's position and orientation. Then we have the explored area that is the union over the trajectory of this visible area. So to summarize, we have the robot's trajectory, we have the range of visibility of the sensors, and we want to estimate the explored area and the coverage measure, so how many times each point in the space was sensed. And we can, of course, define the explored area as a set of points whose coverage measure is bigger than 0. Okay, and so now how do we approach this problem? So from the knowledge of the robot's trajectory and of the visible area, we are going to be defining what is called the sonar's contour, that is defined here in red, and that we call gamma. And gamma is a continuous closed curve in the plane. And the fact that gamma is a closed curve in the plane allows us to use some interesting properties that you might know. So for example, the winding number. So the winding number in a nutshell is how many times a closed curve in the plane surrounds a point in a counterclockwise manner. So for example, if we take the circle that is counterclockwise oriented, all the points in the light gray area, they have a winding number of +1. And here, since it's clockwise oriented, the winding number of the points inside are -1. And for the dark gray area here, we have points that are surrounded twice in a counterclockwise manner. So their winding number is value of 2. So we will be calling a winding number by eta of a closed curve gamma, that for us is the sonar's contour, with respect to a point that it's an integer. Okay, so in this work, we will be proving that the coverage measure of a point P, so how many times this point was explored by the robot, is equal to the winding number of the sonar's contour with respect to this point. And then we will be determining the explored area as a set of points such that the winding number of the sonar's contour with respect to this point is bigger than 0. So visually, we can see at least that this is true. So the points in the dark gray area, they have a winding number of +2 and they are surrounded twice. And the same thing for the points in the light gray area. So now I will quickly discuss the proof of this theorem with you, but of course it will be much better detailed in the paper. Okay, so for this, I need to define 2 new terms that come from sonar imagery terminology. They are the waterfall and the mosaic spaces. So the waterfall space is basically the world in the robot's point of view. So here we have in the axis the lateral distance to the robot, and on the ordinates the time of exploration. So that is why it's called the waterfall space, because it looks like the waterfall image that we had previously. And then for the mosaic space is the world as we know. So it's where the robot's trajectory, the sonar's contour, and the explored area are defined. Okay, so let's take a point here in the mosaic space, so a point P. So the number of times that this point was explored by the robot corresponds to the number of times that this point appears in the waterfall space or in the waterfall image. So for example, this point will appear twice in the waterfall space. So if we take the inverse of this, so here is a mapping function from the waterfall space to the mosaic space. So this point will appear twice. So you can understand, so imagine that the first time that the robot sees this point is at the beginning of the exploration and closer to the left sonar. So that's why we have something like this, like P1. And then the second time that it sees it will be towards the end of exploration and closer this time to the right sonar. So that's why we have something like P2. Okay, so we will be using this. So we start by defining another function, so fp, that is basically the mapping function f shifted by p, so p a point in the mosaic space. And I'm doing this because I want p to become 0, so you see why. And as we mentioned, so the number of times that p is seen by the robot is equal to the number of times that it will appear here. So we have that the coverage measure of the point p would be equal to the cardinality of the kernel of the inverse of fp. So the kernel of the inverse of fp would be a set of points in the waterfall. They are mapped into p by f, and they are mapped into 0 by fp. So it would be a set of points with k points, for example. So the cardinality would be equal to k. That would be equal to the coverage measure that we are trying to estimate. That in this example would be equal to 2. So I'm not going into details here, but by definition, the topological degree would be equal to the sum. So it's the sum of the sign function of the determinant of the Jacob matrix of the map function fp with respect to the points on this set right here. So basically, the sign function would be +1 if fp preserves orientation at pi, and -1 if fp reverses orientation at pi. And we will be assuming that fp always preserves orientation in this work, at least for the moment. So this means that this topological degree would be actually a sum of +1s. So the number would be actually a sum of elements that are in the kernel of the inverse of fp. So it's equal to the number of elements, to k, that we said was equal to the coverage measure. And if I didn't lose you yet, so we have that this topological degree in the plane is equal to the winding number. So we can rearrange the winding number so in terms of f. So it basically is saying that the winding number of the sonar's contour with respect to p is equal to the coverage measure. That's what we wanted to prove. So maybe it was too quick for a proof, but I mean, if there's something bothering you, I will be happy to discuss it later. Okay, so to rearrange the problem, so we have the sonar's contour. We want to estimate the explored area, the coverage measure, and for this, we are going to compute the winding number of the sonar's contour with respect to all the points in the plane. So I will tell you right now how we do this efficiently. And we will be using some interval analysis. Okay, so of course there are some hypotheses that we have on the sonars contour, so on Gamma. I won't be discussing all of them, but the three most important so we can understand the end of the presentation is that, like I mentioned, Gamma is continuous. Gamma has a finite number of crossing points, so of self-intersections, and it only passes through each crossing point twice. Okay, so we start by constructing a CW complex from the cycle Gamma. So we will be interested in the 0 cells and on the 2 cells. So as you can see, Gamma will divide the plane into a finite number of regions that are bounded, with exception for the exterior. And each one of these regions will have a winding number value. So we are going to be estimating the winding number for each one of the regions. And we are going to do this using two rules that I will present right now that will allow us to determine the winding number of all of the regions by knowing the winding number in only one of them. Okay, so the first rule is the Mobius combinatorial rule for defining the winding number. So Mobius states here that if we have two regions that share a boundary, their winding numbers can differ only by one. And since by convention, since we are counting counterclockwise cycles, we will have that the winding number of the region on the left with respect to the orientation of the curve would be the bigger one. So if we have a region like this one that has a winding number value of p, so p being an integer, since it's on the left, considering the orientation of the curve, the region on the right has to have a winding number of p minus 1. And we can propagate this again to the right again, so we are doing p minus 2. Okay, and the second rule is the Alexander numbering rule or algorithm that also uses the Mobius rule, but it will allow us to determine the winding number in all of the regions only by analyzing the self-intersections. So a self-intersection, considering the hypothesis that we determined for Gamma, would be dividing the plane into 4 different regions and would be characterized by 2 lines that cross each other at some point. So what it does is that we can choose one of them. So I'll be choosing the solid line first. And you can see that the self-intersection is dividing this line into 2 edges. So we start with the first one, considering the orientation of the line. And we are going to number the regions that surround this edge using Mobius. So we're going to be numbering these 2 regions. So again, the region on the left will have a winding number of +1, considering the region on the right. And then what Alexander says is that if the next line that characterizes these self-intersection is coming from the right with respect to the orientation of the first one, we can propagate these values that we have here to the next regions doing -1. So p + 1 becomes p and p minus 1. So it's also considering the same Mobius rule that the region on the left should have a winding number of +1. So another example, it's the same thing. It's only, so we start again with the solid line. We are going to number the first edges according to Mobius. So we have p on the left and p minus 1 on the right. And then the dashed line is coming from the left this time. So we are going to propagate doing +1. Okay, so our algorithm consists of first detecting the self-intersections. That this was done when we constructed the CW complex from this curve. So here we have a finite number, like I mentioned. So we have V1, V2, V3, and V4. And then using the self-intersections, we can number all the regions on the plane using Alexander algorithm. So we start with V1. We could have started with any one that we wanted. We are going to start by, like I said, numbering according to Mobius, and then we propagate considering the direction that the other line is coming. So I'm going to go quick here. And once we have all the regions numbered, we can stop. We don't have to do all the self-intersections. We can't, but it would be ambiguous. So now we number all the winding numbers of all the regions considering a variable p. But we know that the exterior has a winding number of 0, so the unbounded region. So p must, in this case, p P needs to be 1. And then we can have the winding number values that we wanted. Okay, so now that we determined the winding number value of all the regions that we have in the plane, we are going to be constructing some sets with this. We are going to be constructing sets that I call SI. So I is considering the winding number value. So for example, in the previous example, we will have the set S1 with points in the plane that have a winding number equal or superior to 1. And we will have the set S2 with points in the plane that have a winding number equal or superior to 2. And then we are going to be using a theorem from McIntyre that allows us to compute the winding number using the sets that we just defined, so as a sum of the characteristic function of the sets. So in the previous example, the winding number would be equal to the characteristic function of the set S1 plus the characteristic function of the set S2. So the characteristic function of a set Si at a point P is equal to 0 if this point doesn't belong to the set, and equal to 1 if the point belongs to the set. So if you take this point here, P, the winding number will be 2 because it belongs to all the set. This point here belongs only to S1, so the winding number is 1. And what happens if the point is in the border of one of the sets? So usually in the literature, in this case, the winding number is not defined. However, for us, a point that is in the border of the sonar's contour is a point that was observed by the robot, so it is a point that was seen at least once. So for us, in this case, the winding number is defined, and for this point would be equal to 1. Okay, and like I mentioned, we are going to be using interval analysis to characterize the area quickly and efficiently. So we are going to be computing the winding number with respect to boxes. So what changes is now is that the characteristic function of the set would be the singleton interval 0 if this box doesn't intersect the set, the singleton 1 if this box is a subset of Si, and 0, 1 otherwise. So this box here has a winding number of 1, and this box has a winding number that is an interval 0, 1. Okay, so now some results. So for the simulation, we used the Kodak library. So in red, we have the robot's trajectory, and in blue, we have the sonar's contour. And this is the characterization of the explored area that we obtain using interval analysis. So how do we do this quickly? We start with the big box, and we calculate the winding number for this big box. If the result is not a singleton, we bisect the box till we obtain the precision that we want. So here I chose a big precision so we could see the uncertain box. So uncertain boxes are boxes whose winding number is not a singleton. So we have boxes in green that have a winding number of 1, boxes in blue that have a winding number of 2, and in black, this means that we have points with different winding numbers inside the same box that we can calculate too. So we can determine, for example, the points with a winding number between 0 and 1, 0 and 2, and 1 and 2. And here, if we are only interested in characterizing the explored area, a point that has a winding number between 1 and 2 is a point that was surely explored because it was seen at least one time. Okay, so we also use some data that was acquired by a real autonomous underwater vehicle. So this is DOHAD. So DOHAD has 2 side scan sonars that are mounted like the ones that I previously showed in the pictures. And for proprioceptive information, it has a DVL, so it's a Doppler velocity logger that is used to estimate the robot's speed underwater using acoustics. Then we have an inertial measurement unit that will give us angular velocities and accelerations. And we have a pressure sensor that will be giving us the depth of the robot. And why do we need this? We need this because till now I was telling you that the range of visibility of the robot was fixed, but actually it will depend on its altitude. Okay. And we could take the data that this robot acquired during a mission in the roadstead of Brest. doing a classical survey path that I will show to you right now what it is, in a small mission of almost 50 minutes. So this is the classical survey path or long path. So we obtain this trajectory by integrating the data, the proprioceptive data that we had here. So again, we are not considering the error in the estimation that, of course, in 50 minutes becomes pretty big. And then here we have the sonar's contour. So you can see that the altitude of the robot was almost stable. I mean, it changes a little bit around here, but not too much. And this is the characterization that we do of the explored area. And again, we can compute this very quickly using interval analysis. So we have regions that were observed once, twice, and 3 times. Okay. So to conclude quickly, so we can determine the explored area and the coverage measure using the winding number and also using interval analysis. And the fact that we use interval analysis, it makes our work adaptable to deal with the uncertainty in the robot's trajectory that we will be doing in the future very soon. And for future work, we would also like to understand how our work relates to other works where people work with robotic and topologies at the same time. So for example, we are going to be using a multiple robot system to doing the coverage measure, and we would like to understand how we can do this and how we can integrate, for example, the different sonar contour that we are going to obtain. So I think that's it. Thank you for your attention.
I guess I had a question about because you said that you know what the depth is, right?
Yes.
But essentially, if you stay at the same depth, but the sea bed is not flat, then you'll also have this.
Yeah, that's a good question. So actually, we were in the roadstead of rest, where actually we have the luck of know very well the bathymetry.
Okay. Yeah.
So that's it. I mean, if you're going to a place where you don't know the bathymetry, you'd have to add other sensors to estimate this too. Yes.
Okay. Then we have more sensors, I guess.
Yeah, exactly. Because the depth will be determining the depth, but what we need, like you mentioned, is the altitude. So if we don't know the bathymetry, it's complicated. So we can estimate with acoustic rays, for example. But yeah, it's something that can be done. But in this case, we could use only the pressure because the bathymetry of at least of the roadstead is well known.
Other questions? Oh, let's play this again.